Hello, everyone. Welcome to the first lecture of Fluid Mechanics and Hydraulic Engineering course in this semester. Um, so, in this lecture, I'm going to give you some brief introduction about fluid mechanics, what's the difference with previous courses that you had, for example, solid mechanics, or other courses like mechanics courses that you had during your bachelor studies in civil engineering. So I'm going to also give you some important parameters in fluids, three different parameters that we will be mostly working on this semester. And then we are going to introduce the dimensions, units that we will be mostly using in this course. And also I would give you some notes about dimensional homogeneity, which is kind of important in this kind of problems. And then we will move forward to the system of units and other important topics that we will cover later on. So this is the first few lectures will be mostly on introduction to fluids, and then later on we will start working on some problems like starting with hydrostatics, and then we will go to dynamics later on in the course. And the first half of the lecture we will focus on the fluid mechanics part, and then in the second half we will go to the hydraulic engineering section, which would be mostly engineering. So the first half is mostly kind of theoretical and background of fluid mechanics. It will give you this kind of background about the mechanics of fluids, which is kind of a new topic for you. And then the second part will be mostly engineering side of that, which will be used for designing different open channel flows, which are very common in civil engineering major. Okay. So let's get started. So fluid mechanics in general is a subset of a bigger field, which is applied mechanics. Okay. Of course, this field has a lot of applications. For example, and also topics like solid mechanics, even some other type of atomistic mechanics and other type of kind of mechanical fields that it involves and it includes. Okay, so this is kind of a subtopic of that bigger field, and which is kind of focused on understanding and predicting and modeling the fluid phenomena, the fluid flows. Okay. So in particular, we will focus on understanding the behavior of liquids and gases. Okay. So some important parameters in fluids that we typically use are as follows. One, size of the flow. Or L, we show it with L2. Okay, and what does this mean? This is a characteristic length. Okay, a characteristic length of a flow. So for example, if you have a pipe flow, which is one type of flows that we will investigate in this course, imagine this is a pipe, okay? So the size in a pipe the size of the flow, or L, is proportional to what? To the diameter of the pipe, right? So, or pipe diameter. So the size of the flow, or L, here is proportional to this diameter here, which we call it as D, okay? So for example, this pipe can be oil pipe, or different things, like it even can be your veins. And any pipe you can see, like even water pipe, oil pipe, or different types of pipes, or different type of systems that look like fluid systems that look like this. So the characteristics length of the flow in this type of systems, or the size of the flow actually in this type of systems, is proportional to the pipe diameter, okay? Also, for example, say we can have different things. This is just one example. And for example, if you have a channel flow, say you have a channel like this, and I'm drawing it three-dimensional. Say you have a channel flow here, that the flow is coming, the fluid is coming from this side. So there are different, the major characteristic lengths here that we like use would be this height or depth of the flow here, okay? So for example, we can show it with H, okay? So L is gonna be proportional to this depth of the flow, okay? So these are different type of flows, and this is like, this can be continuous, okay? Like a channel flow that we will investigate later. So this is just an example to show that what is the size of the flow, okay? And we will go through in more details later on when we will discuss the important parameters, like what is important, for example, in hydraulic engineering later in the second section of the course. This depth of the flow will be very important. In pipe flows, this diameter would be very important, and in any type of flow, this size of the flow is very important parameter, okay, that we take into consideration. The second important parameter in flows and fluids is speed of the flow. Which we show it with V, okay? For example, wind speed. For air. So for air is also a type of flow, right? Fluid is a gas. So for air, the speed or of the flow would be wind speed, okay? That you almost every day you can, if you go out, you will kind of feel that the wind speed when it is high or low, okay? So that is called, we call it speed of the flow. And also for these, for example, pipe flows, they also have some speed, right? They go with they flow in kind of a pipe or a channel, so they have kind of a speed, and we call that speed of the flow. And that's also a very important parameter in our kind of fluid mechanics problems. The third important parameter is pressure. So this is probably something new that we will, it's very important in fluid kind of problems, and we call that as we show that with P, pressure or P. An example of that is, think about that. Something that you might not consider, but that's also very relevant, is blood pressure, right? You have heard it in different medical contexts. Blood pressure, blood is also kind of a fluid, okay? And the pressure of the blood, we show it with P, and that's an important fluid parameter, okay? Another thing, for example, as for pressure of the fluids, could be car's tire. Right? You have to check the pressure of your the car's tires, right? And that is the same thing, the same phenomena that is used in fluids. That's the pressure of a fluid. And that is a pressure of gas, right? Blood is a liquid, and that's a gas. And then the other important thing that is very important in this context is atmospheric fluid, atmospheric pressures. So atmospheric pressure, right? Of course, like if you have different elevations, the atmospheric pressure will be different at different elevations, right? So for example, if you are like on top of a mountain, the pressure would decrease, and then as you come down like to the sea level, the pressure, atmospheric pressure or air pressure decreases. So this is something we call, and is important for us, one of the important parameters in fluid. So these are three important parameters that we typically work in any fluid problem. Size of the flow, speed of the flow or V, or pressure or P. Okay. So I just want to give you a general statement about the application or importance of this kind of fluid problems. So as an engineer, you'll be involved in the analysis of systems that require good understanding of fluid mechanics. In particular, for civil engineering problems, as a civil engineer, there are multiple problems that you need to have a pretty solid understanding of fluid mechanics, and those include hydraulic structures, dams, urban water systems, oil pipes, open channel flows, etc. Okay? So these are some examples that as an engineer you need to have a very solid understanding of fluid mechanics to be able to tackle them. Okay. So now I want to give a broad question about the difference of fluids and solids. Okay. So the question I have is, what is the difference between a solid and a fluid? So, can you think about that for a moment? Think about that yourself. What do you think? What's the difference between a solid and a fluid? What really distinguishes a fluid from a solid? Can you think about it? So, a kind of informal definition of fluid, which kind of distinguishes it from solids, is as follows. A fluid is defined as a substance that deforms continuously when acted on by a shearing stress. Okay, what do I mean by this? This means, so let me, before doing that, also define, before explaining this, I want to also define solids, and then I will explain this, what do these mean. Solids like steel will initially deform, but they will not continuously deform. When acted on a shearing stress, okay? What does that mean? What is the difference? So the difference here is something about the deformation when we add a shearing stress on the problem, on the body, or in the body of a fluid or body of a solid. Okay, so let's see what is the difference. The difference is here. So imagine you have a solid substance, like for example steel or anything, any cubic. Okay, when you add a, say, shearing stress on this, or a force here on this solid, what happens to that is it might initially deform, okay, to a new type, to a new shape. Something like this. But it will not continuously deform. It will just stay there, even with that initial force, okay? Unless you increase the force, okay? If you don't increase the force and you just keep it a constant value, say for example 100 Newton, okay? It will just deform and then it stops. However, in a fluid, so say here we have a fluid, okay? You have a channel, something like this. Like water. So if you add a force here, like say 100 Newton to this fluid, so this is solid, and this one is fluid. What happens? Think about it. When you add a force to a fluid, even a kind of not too big force, like a average force like 100 Newton, which is not that much that big, right? You can even put it with your hand. What's going to happen? It will continuously deform. It's not like it will deform something like this and then it will be like, it will stay there. It will stop. It will continuously deform because the molecules in fluids, unlike solids, are not kind of stuck together that much strong, like, right? So it will just continuously deform, and it will find actually a velocity. It will find a speed once you act or apply a shearing stress into that, okay? So it will find some kind of a velocity profile like this that we will show it later on in the course, but a velocity profile like this. And the reason it is like this is because near the surface, it is kind of attached to the surface, so the molecules are not gonna move that much, but as you go along to the free surface, it will just go with the highest speed that it can, okay? Based on the imposed force here. So it will continuously deform. It will not keep and stop deforming. So this is the major difference between solids and fluids, and that is because a fluid is a substance that deforms continuously, as you can see when we apply a shearing stress or force to that, while solids will initially deform like here, that is shown here, but they will not continuously deform. Okay? So this is the major difference between a solid and a fluid. So now I want to talk about another important topic after these introductions about fluids, fluid mechanics, fluids and solids, about dimensions and units that we will be using in this course and are also important. So let me start it here. So dimensions and units. So we can describe any quantity using primary quantities such as a length. So we have some primary quantities. We can show any quantity, at least in this physics, fluid mechanics, and also in most of the mechanical engineering and mechanics problems that we have with these primary quantities. So length, you can show it, we show it with L. Time, or T, mass, or M, and something that we don't typically use in this course, but it's like it's all important for fluid mechanics, especially thermodynamics, is temperature. That we show it with theta. Any quantity that you find in this physics, most of the physics problems that you have seen, other than like electromagnetics or other things that we don't work on those, but these kind of mechanics, especially fluid mechanics that here we have, can be described as these primary quantities: length, time, mass, and temperature. So these are primary quantities, or also we can call them as basic dimensions. Okay. So these can be used to describe any other secondary quantities such as velocity, acceleration, even something like pressure, which is very important in fluids, right? An important parameter in fluids that we discussed. Okay? All of these can be described using these primary quantities. So, let me show you an example. Example. Describe area, velocity, force, and stress using primary quantities. Okay, let's see. So area can be described, and by description of this we show it with equal and also a dot sign on top of that, equality sign. So what is area? An area is like a length square, right? You multiply, for example, if this is 3 meter and then this is 4 meter, what will be the area of this? It is 3 times 4, which will be 12 meter square, right? So you are multiplying two lengths, the first length and the second length, correct? So this secondary quantity can be shown with the first quantity as L, length, times L, or lengths, which will give us length square, correct? So this secondary quantity in terms of primary quantity will be will be L square. Okay. How about velocity? Velocity, or V, we can show it as what? It is meter per over second, right? That is the unit. So in terms of dimension, that would be length over time, right? So I can show it with L over T, or L T minus 1. And the way we call it is, or read this, is the dimension of velocity equal length divided by time. Okay? The second thing, the third thing is force. The force, or F, right? Okay. In order to describe this in terms of primary quantities that we have, which are length, time, and mass, I'm going to use Newton's law. So Newton's law states, second law, states that force equals to mass times acceleration, right? So the dimension of force should be what? Should be mass times acceleration, and acceleration is what? Is length over time squared, right? Velocity is length over time, and acceleration is going to be length divided by time squared. So it's going to be time squared, or we can show it with mlt minus 2. This is the dimension of force, which is a secondary quantity. Okay, for this one, I want to give some time so you can do it yourself, and that is stress. So I just write the definition, and I give you 1 minute to solve it yourself. So stress is force per unit area. So find this yourself. Okay. You have 1 minute to do that. Okay. So let me write what it would be, and then you can check whether you are right or not. So stress, we can show it with sigma. It's going to be force per unit area. So what was force? The force was mlt minus t minus 2, right? That was the dimension of force. So I'm just going to write that, mlt minus 2. Okay. This is force the dimension of force per unit area. So this is going to be over L squared, which is what? Which is area. We had it here. So this is mlt minus 2, or force per unit area, or L squared. So what it would be? It will be m. This will to cancel out, and we will only have one L here. So it's going to be m L minus 1 t minus 2, correct? So this will be sigma, or stress. The dimension of that, which is a secondary quantity described as from the dimensions of the primary quantities. So these three quantities. Okay. So let me review what we have done in this section, and in the next lecture I'm going to talk about dimensional homogeneity, which is very important in any physics problems, and especially in fluids, because there, if you learn that, you will never make a mistake in equations that you write in fluid mechanics. And after that, we will talk about system of units, like international system, or SI, or British system, gravitational system. And then we will briefly talk about ideal gas law, viscosity. And then after all of these, this will finish the kind of a little bit we will talk about Newtonian fluids, and these finally will finish the first chapter. We will finish it probably not the next lecture, but probably in 2 lectures we will finish that, and then we will go to the second chapter, which will be fluid statics. Okay. So let me go through what we have learned today. So first, we define fluid mechanics, important parameters in fluid mechanics, which are size of the flow or length, which we showed with L, a characteristic length, speed of the flow, which we showed with V, pressure, which we showed with P. And then we talked about different applications that you need fluid mechanics, like for hydraulic structures, dams, urban water systems, oil pipes, open channel flows. I probably have forgotten to write this here. Let me correct it. Open channel flows, etc. Right? And then we define what is the difference between a fluid and a solid. And we talked about this deformation when you act force, a shearing stress on both fluids and solids. So in solids, they initially deform, but they will not continuously deform. Okay? In fluids, they will continuously deform when they are acted on by a shearing stress. Okay, so this deformation, whether they deform or not under a shearing stress, is a difference, kind of informal or semi-formal definition of solids and fluids. Then we talked about dimensions and units. So we can describe any quantity using primary quantities, and these are the primary quantities that we have: length, time, and mass. And then these can be used to describe any other secondary quantities such as velocity, acceleration, and pressure. And then we solve an example in which we describe these variables, these secondary quantities, using those primary quantities. Like area was shown as L squared, velocity is LT minus 1, force is MLT minus 2, and stress is going to be force per unit area, so it's going to be ML minus 1, T minus 2. Okay. Thank you very much, everyone.